Let's go into some more detail about covalent bonds. Now, you know, a covalent bond occurs when you have a sharing of electrons. What we find is that there are cases where the sharing is even and other cases where that sharing is uneven. Let's look. Bonding electrons are shared evenly between two identical atoms. Let's say, for example, you have a hydrogen atom and a hydrogen atom. Now, you've got the electrons that are being shared between those two atoms, and because it's sharing, we call that a covalent bond. And, oh, hey, look at this. You're seeing it looks like a whole bunch of electrons between those two hydrogen atoms. That's a probability cloud. We call that from chapter 5. This is merely showing where the two electrons of the covalent bond tend to be over a given period of time. So say you're one of those two electrons being shared. And you situate yourself right in between those two hydrogen atoms, and you look one way over here, and you look the other way over here, and you essentially see the same thing. The nucleus is the same. There's a +1 proton over there, there's a +1 proton over there. Which side are you going to go to? Well, more technically, we would say that this hydrogen has an effective nuclear charge of +1, and this hydrogen has an effective nuclear charge of +1. And if you're one of these electrons, you're going to spend more time over here or more time over there? Well, both sides are the same. You're not going to be pulled to one side or the other. On average, you'll be distributed evenly between those two hydrogen atoms. Contrast that now to a case where we have a hydrogen bonded to a fluorine. The hydrogen has an effective nuclear charge of +1. The fluorine has an effective nuclear charge of +7. All right? So you're an electron situated between a hydrogen and a fluorine. You look over there, you see, +1. You look over here and go, oh, +7. You're an electron. You're negatively charged, and you see a +7. What do? Over to this side. So here's a case where the electrons are not going to be shared evenly. We see how it is that the fluorine has a greater pulling power. It can tug on those bonding electrons better than can the hydrogen. So in this case, the electrons are not shared evenly. So here's a case where they're shared evenly. Here's a case where they're tugged to one side, and we say that the electrons are not shared evenly. How do we represent this? We've got these symbols up here, delta positive, delta negative. Let's go over to this side first. You come up to this fluorine atom, and you see that there are electrons hovering around that fluorine atom. Why? Because of the greater effective nuclear charge. And you sense all these electrons. What's the charge on an electron? Negative, all right? So you're seeing there's this negative character over here. And we can describe that by using this symbol up here. This is the delta negative symbol. The Greek letter delta is used to indicate slightly. So we say slightly negative. This side of the atom, side of the bond, is slightly negative. Now, if the bonding electrons are pulled to the fluorine side, what about the hydrogen? The hydrogen, the electrons are being pulled away from it, so that hydrogen's nucleus is somewhat exposed. The nucleus is positively charged, right? So whereas this side's slightly negative, this side becomes slightly positive. And you know what? As much as this becomes negative is as much as this side becomes positive. So we have this separation of charge. One side is negative and the other side is positive. Another way to indicate that is to use an arrow that's crossed. And the arrow always points to the side that's slightly negative, and the cross side is the side that is slightly positive. So this is all a consequence of an uneven sharing of electrons. This is the term used to describe a case where you have a separation of charge, where one side's negative and the other side's positive. Why don't negatives and positives just come together? How is it that they remain separated over the length of a bond? It's called a dipole. That's what it is. When you have a separation of charge, it's called a dipole. Not dipole, it's a dipole. And why is it that you get a dipole? Well, you get a dipole when one atom has a greater pulling power than does the other atom. It's the difference in their ability to tug on those bonding electrons that gives rise to this dipole. And this big fancy term behind me right here is the term that describes the ability of an atom to tug on bonding electrons. Electronegativity, perhaps the longest term used in this book. A measure of how strongly an atom is able to tug on bonding electrons. Rather than saying electronegativity, you might find me and yourself and your instructor saying pulling power. Electronegativity is the pulling power that an atom has, for the bonding electrons. And we saw briefly in chapter 5 that electronegativity is a periodic trend. Elements to the upper right tend to have the greatest electronegativity, aka pulling power. The atoms to the lower left tend to have the smallest pulling power, or electronegativity. And as you move from one side to the other, it gradually increases. You might see electronegativities depicted in a two-dimensional periodic table with just the numbers here. These numbers represent the electronegativities. And they are given on a scale of 0 to 4. And where those numbers come from? They came from laboratory experiments. So they went to the laboratory and they measured the pulling power of the various atoms. And the one with the greatest pulling power, fluorine, they gave it the value of 3.98. And the one with the weakest pulling power, they gave it a smaller value. It's like 0.6 or something like that. And these are the values reported here. A special note should be given to hydrogen. Hydrogen's over here. It actually has an electronegativity that's comparable to the atoms over there. So what we do is we take the hydrogen and slide it over to where it has the same electronegativity between boron and carbon. Hydrogen has an electronegativity of 2.2, which is comparable to carbon, is 2.55.